So we're gonna move from thinking about hedging the market or the S&P 500 with synthetic options and using data that runs way back in time, so interesting historical data, to hedging exotic options using the latest technologies available, so reinforcement learning as part of the machine learning and AI breakthroughs. And to talk to us about that, we have John Hull of the University of Toronto. And the discussant will be Andrew Lowe from MIT.
Well, thanks very much. It's a real honor to be here. I have to say that paper that was published, or those papers, I should say, that were published 50 years ago have had a huge effect on my life and my research, my career development, and everything. So thank you both very much. So yeah, this paper I'm going to present, Hedging Barrier Options Using Reinforcement Learning. There's actually a little bit of difference between the title here on my slide and the title on your program. It's the title on the program is Hedging Exotic Options Using Reinforcement Learning. I guess the situation is that right now we're just talking about barrier options, but we have high hopes that we're going to generalize a bit. So okay, we're not doing something right here. Oh, there we go. MIT technology is not what it's. My hands are not functioning terribly. Whoops. I'm supposed to press this green button, right? Oh. Which one do I press? Here, oh, that's the one to press. Okay, beg your pardon. Exactly. Okay. It's okay. I think I can probably manage. Okay, so as you can see, we've got quite a few co-authors for this paper. Pleased to say that one of my co-authors, Jackie Chen, is over there at the back. He can answer any really difficult questions you have at the end. There's 6 of us all together. We have this research group called FinHub at University of Toronto, and we seem to get more and more people joining it all the time. So the papers that we write tend to have lots and lots of co-authors. And also we have a mixture of people from the business school, from the engineering faculty, and practitioners. And in fact, this particular paper, if you look at the co-authors, 4 of the co-authors are practitioners and 2 are academics, as it happens. This is an area we've been working in for a while, and so we've got 2 earlier papers on it, which I'll have something to say about as we go along. Those have both been published. So okay, so this is not new to everybody in the room, of course. We've had traditional hedging approaches for derivatives and other options for quite a long time, and we have these Greek letters: delta, gamma, vega. I guess vega's not really a Greek letter, but we call it a Greek letter. And how do these Greek letters work? Well, periodically, we look at the Greek letters and we either set them to 0 by taking an appropriate position, or certainly move them in that direction. And really what we're doing is setting up an instantaneous hedge. We're thinking that if there's a change in the value of the underlying market variables over the next short period of time, a small change over the next short period of time will be okay if we hedge. We're not looking at a longer period of time, and we're not looking at big changes. So the implicit assumption is that each time the hedge position is rebalanced, the objective is to minimize the change in the value of the portfolio over the next very short period of time. Now, of course, if this didn't work well, people wouldn't do it. So obviously it works well. But what we're doing on this paper is looking and seeing, is there some other approach that can be used? So this is where this thing we call the RL alternative. RL is short for reinforcement learning. And it's, this whole machine learning business is something that I got into recently. So we develop a longer term hedging strategy. So we don't just look, as you could say, an instantaneously short period of hedge and say we want to make sure we're hedged over the next instantaneously short period. We say, yeah, we know we're going to rebalance every day, but, let's look 10 days ahead, let's look 20 days ahead and make sure that we're setting up a reasonable hedge. So what are the potential advantages of this? Well, one of the potential advantages is that, as you'll see, you're free to choose your objective function. If you think about delta hedging, for example, what you're implicitly doing with delta hedging is saying that, gains, you want to eliminate gains just as much as you want to eliminate losses, because you want to sort of maintain the value of your portfolio. And that may not be what you want to do. You may be much more concerned about losses than gains. And the reinforcement learning alternative allows you to do that, as we'll see. You have lower transaction costs. And if as a trader your performance is assessed, say, every quarter or every month, then you can set an objective that corresponds to that. So what is the reinforcement learning approach? It's designed for multi-period decision making. So it's designed for situations where you make a decision today, the world changes, you have to revise the decision tomorrow, the world changes, you have to revise the decision the next day, and so on. It's a general tool in machine learning for solving those sort of problems. And that, of course, is exactly the sort of problem that we have when we're hedging derivatives. We set up a hedge, the world changes, we rebalance the hedge, the world changes, we rebalance the hedge, and so on. So, I'm not going to be talking a lot about the actual algorithm that underlies reinforcement learning. It's actually in one of our earlier papers if you're interested. But just think about it as a clever trial and error approach. Okay? You want to develop a strategy, maybe over the next 20 days, for hedging your portfolio. Let's start with maybe a random strategy. Let's improve it a little bit, then improve it a little bit more, and so on until we eventually arrive at what seems to be the best strategy to use over the next 20 days. So that's what it's all about. It uses what's called the actor-critic approach, which is an approach that's been developed where you've got the actor that's deciding on the strategy and the critic that is saying, yeah, you should move the strategy a little bit in this direction to improve it. So one of the key points we've made in our earlier papers in this area is that one of the big advantages, for regular options, reinforcement learning doesn't improve the quality of your hedge that much. But what it does do is lower transaction costs. You do less trading when you use reinforcement learning for hedging than you would do if you just use delta hedging or something like that. And if you'll forgive me, I've got a really trivial, almost trivial little example here to illustrate that. I mean, let's suppose you've got a portfolio, it's got a delta of 50, and you're looking at two periods. You know what's going to happen during the first period, and you're uncertain about what's going to happen during the second period. During the first period, delta is going to go from 50 to 70, and then during the second period, it'll either go back to 50 or up to 90. how should you hedge this? Well, we all know how we'd do the hedging if we were using regular delta hedging. The key thing is if you use reinforcement learning, you'd look at the 2 periods and you'd say, well, you know, there's a chance that delta will come back to 50 and there's a chance it'll go up to 90. Maybe we should just wait. We'll rebalance at the end of the second period. We won't rebalance. We won't do anything at the end of the first period. And that saves you quite a lot. In fact, it involves half as much trading when you work it out. So that's, in the 2 papers that we've written so far, that's, you know, that's what we focused on. We focused on how people should seriously consider using reinforcement learning for hedging because it'll save you a lot on transaction costs. And we've quantified that. This research is a little bit different because we're not looking at regular options. We're looking at exotic options. In particular, in this paper so far, we've looked at barrier options. And we're interested in whether reinforcement learning can improve hedging for barrier options. And we suspect, or we know, that it's going to improve things as far as transaction costs are concerned. So, you know, barrier options are kind of interesting. They've got this discontinuous delta. This is a picture of a down and out put. The barrier's at 10, strike price is 11, the volatility is 30%, and it's a 10-day option. So you can see that the delta sort of jumps up at the barrier. So you can sort of, just looking at that, you can say, well, probably delta hedging doesn't work that well because it's got this discontinuity. When you're getting close to the barrier, you don't really know what to do as far as delta hedging is concerned, particularly when you're hedging discretely, say every day, as you nearly always are. So that's the sort of situation we've been looking at in this paper so far. We compare three different hedging strategies for a short down and in put. So this is something which, when you reach the barrier, it becomes a put option. But if you never reach the barrier, then it never becomes a put option. Okay, so you're selling a you're selling a down and in put option. And we look at 3 different hedging strategies. We look at regular delta hedging. We look at what we've called myopic hedging. This is where you look a whole day ahead. And you say, okay, what's the situation going to be like at the end of the day? Because I know I'm going to rebalance my portfolio at the end of the day. And given my objective function, which I'll tell you about in a minute, what should I do during the day to do as much good as I can as far as that objective function is concerned? And then we've got reinforcement learning hedging, which is where you look several days ahead and try and come up with a hedging strategy over a period of time. In fact, over the whole life of the option. So we look at 2 different objective functions here. We've got, I don't need to explain to people in this room what these objective functions are. Value at risk with 95% confidence and conditional value at risk, if you prefer, call it expected shortfall or expected tail loss. Call it CVAR 95, which is, of course, the average loss if you're in that 5% tail of the distribution. So we're assuming that the hedger's objective function is focused entirely on losses. Okay, and basically is trying to minimize losses as much as possible. You can come up with other objective functions. You might want to say, well, not only do I want to minimize losses, but I actually want to give some benefit to gains. So you could sort of, you know, and a colleague of mine in the statistics department, at U of T has done that. So here's some illustrative results. Let's walk over here. I can see them more easily. But so we've got, we just had to choose some parameters to sort of illustrate what was going on. The asset price starts at 10.6. The barrier's at 10. The maturity is 20 days. The volatility is 30%. The options on 100 units of the asset, and we rebalance daily. Okay? So, and as I said earlier, we're comparing 3 different hedging strategies. One is delta hedging, one is this myopic hedging, where we're looking 1 day ahead, and the other is reinforcement learning, where we're looking at multiple days ahead. And there's a strike price, of course, for this option, and we're looking at strike prices from 10.2 to 11. And just looking at the table, you can see that reinforcement learning consistently outperforms delta and myopic. So here it's not a transaction cost consideration, because we're assuming no transaction costs. It just does the hedging better than either delta hedging or myopic hedging. Generally speaking, you can see that what you could sort of argue is the gain more for CVAR than it is for VAR and that sort of thing. But generally speaking, it does pretty well. And as the strike price increases, so reinforcement learning does relatively better because, of course, there's much more at stake when the strike price is 11 than when the strike price is 10.2, because if you hit the barrier when the strike price is 11, you've got a deep in the money put. So where do those improvements come from? So we sort of analyzed what was going on, and near the barrier, it underhedges relative to what delta hedging would do, because it recognizes that if the barrier is breached, and after all, we're only hedging we're only rebalancing once a day, so there's a non-zero probability that we'll hit the barrier in the next day. So it recognizes the barrier has some non-zero probability of being hit, and if the barrier is hit, then delta will decline. So, and in fact, this is what traders tend to do with barrier options anyway. Under hedge as you get close to the barrier. As it moves away from the barrier, and you can say when it's in sort of intermediate points, there's some chance of the barrier being hit, but it's not a huge probability. It tends to overhedge then, because the cost of overhedging is small and there are potential future benefits. So those are the 2 differences we observe between what reinforcement learning does and what regular delta hedging does. We've carried out some robustness tests, because one of the things about reinforcement learning is that you've got to have a model for how the asset price is going to evolve. So we assumed that you developed your reinforcement learning model assuming volatility was going to be 30%, but actually volatility wasn't 30%. Volatility could be anywhere between 10% and 50%. Okay. Now, as far as delta and myopic is concerned, we assumed that they have up-to-date information on where volatility is, so they're using the latest information on volatility, whereas as far as reinforcement learning is concerned, you've just developed your hedging strategy over the next 20 days, and that's it. You developed it on the basis of a 30% volatility. And you can see that, reinforcement learning, I mean, it does okay if volatility is 20% or 40%. In fact, CVAR is okay in terms of producing improvements when the volatility is 10% or 50%. So the small improvements for CVAR in those situations, not for VAR. VAR does slightly worse. But you can see that, so this is a sort of robustness test that we're carrying out, and you can see that, you know, it's, at least as far as this test is concerned, it's reasonably robust. Yes, Paul?
Yeah, I have a question. Is in the case where the volatility is higher, does the RL strategy actually learn?
Well, interesting you should say that, because in these tests it doesn't learn. In these tests you say, we just assume volatility is going to be 30%, and we set up the strategy that way. But that is one of the things we're looking at right now. How can we make the RL strategy dynamic in the sense that, you know, it recognizes it's in a higher volatility environment, and therefore it should revise its strategy.
Right, and I thought that was part of the structure of reinforcement learning and how it would differ from dynamic programs, where if your model is incorrect, it will get updates. It'll learn that it's wrong.
Yeah.
20 days may be too short a period.
Yeah, well, we're certainly looking into that. You've anticipated one of my later slides, as a matter of fact. Yeah. So again, we see the advantages as far as transaction costs are concerned. I mean, we didn't build transaction costs into this model, but we did quantify, you know, we did keep track of how much trading you're actually doing, and you can see that with reinforcement learning, you're doing quite a lot less trading for both VAR and CVAR. So not only in a no transaction cost world do you do better with reinforcement learning, but actually you'll also save money as far as transaction costs are concerned. We looked at some stress testing scenarios, which are, you know, how well does the reinforcement learning model work in really stressed environments? And this is where it's nice to have practitioners on our on our team writing the paper. They tell me that there's two standard sort of stress scenarios that companies are using right now. There's what's called the L-shaped scenario, the L-shaped window, which is the sort of window that's from sometime in February 2020 to March 2020, where the market was going down. It's not exact. Well, it is a little bit L-shaped, and then there's the V-shaped window, which comes after that when market comes down and recovers. And the question is, you know, how well does reinforcement learning do?
Back here.
So we use those two scenarios as tests for how well reinforcement learning does. And we find that reinforcement learning outperforms both myopic and delta. I mean, it makes losses, and myopic and delta makes losses, but the losses were about 20% less for reinforcement learning. And we also found that if you're trying to choose between CVAR and VAR, CVAR does better as a We've also recently looked at the use of vanilla options to hedge barrier options. As you get near the barrier, using a short-dated vanilla option can do you some good. So we've done some tests doing that, and we find that actually the results mirror the results we've got for delta hedging and using the underlying asset for hedging, that it's much better to use reinforcement learning to decide what positions you should take in the vanilla options versus, for example, just to neutralize gamma in a sort of mechanistic way, and gives better results and lower transaction costs. So there's a couple of extensions of this that we're looking at. The second of these is what Paul talked about, which is develop ways of making the strategy dynamic to reflect market changes, which, as you say, is quite possible within the reinforcement learning technology. So that should make reinforcement learning work even better in some of the tests that we did. And the other thing is, the trader needs to estimate a stochastic process for the arrival of derivatives dependent on the underlying asset. So you've got to think not only what derivatives do I have in my portfolio now, but in theory, you've got to think what will I have in my portfolio going forward? What's the stochastic process that's giving rise to the arrival rate of these derivatives? What do derivatives look like when they arrive? The other thing we're looking at is just how important is it to be precise as far as that's concerned? Or can we get away with sort of a rough and ready approach as far as, worrying about what's going to happen in the future and just focus on what we've got right now? So we don't have an answer to these two questions yet. So what are our conclusions here? What are the advantages of using reinforcement learning for hedging? Lower transaction costs, for sure. That's, you can think about sort of 25%, 30%, maybe even 40% lower transaction costs if you use reinforcement learning. You have complete freedom to choose the objective function, whereas delta hedging, as I say, implicitly has this symmetrical objective function where gains and losses are treated symmetrically, which is probably not what a trader actually wants to do. It gives better results for some exotics like barriers than traditional approaches, even when there are no transaction costs. Okay, so you've got the transaction cost advantages overlaid with other advantages as far as barrier options are concerned. You can choose the time horizon to match the way the trader's performance is assessed. So if the trader knows his or her performance is going to be assessed at the end of 3 months, it might make sense to use 3 months as your horizon date in terms of the reinforcement learning algorithm. And the tests indicate that reinforcement learning is pretty robust and gives good results during stressed periods. There's, more tests than those I've presented today that are in the paper. Of course, the disadvantage is that it's computationally much more demanding than traditional approaches. I mean, calculating delta, nice and easy. Delta's additive. You can delta for this derivative, add it to the delta for this derivative, and so on. This is a lot more complicated, but computers are getting faster and faster. Obviously, as academics, we don't tend to have the fastest computers in the world, but we find it takes about an hour to come up with a good reinforcement learning strategy for, for a particular situation. So I think that's all I wanted to say. Thank you.
Okay, well, while my slides are getting loaded, I want to start by thanking the organizers for giving me an opportunity to be a discussant, although that's not quite right because the organizers didn't invite me. They invited Doug Breeden, but Doug unfortunately broke his ankle a couple of days ago. He's undergoing surgery, so that's why I'm here to be the discussant. And I do want to thank the organizing committee, Jonathan Parker, Adrian Verdelin, Debbie Lucas, John Wang, and Lena Kogan for helping to organize this event. And I want to thank John for being here to present. It's really a pleasure and an honor to have a leader in derivatives as part of this gathering. And let me just first summarize my discussion because I'm not going to have much in the way of critical comments. I'll have a bit of exposition to provide context and then maybe a couple of suggestions for additional horse races that they may want to do. But this is an important contribution by a leader in the derivatives literature for reasons that are a little bit different than the traditional sense. From a computational point of view, this is a relatively straightforward paper, But the fact that we're using a particular kind of AI to price and hedge options, I think is pretty significant. Now, John is a consummate expert in derivatives, as you probably know. He's got the leading textbook in options. We're at the 11th edition, is that right, at this point? But more than that, John has actually ventured out from traditional finance. And as he mentioned, he's been spending time actually working on machine learning and other forms of AI. So this is a really unusual combination of skills and interests where finance meets AI in a very computationally intensive and I think useful way. So this is a series of papers that's going to usher a new literature in applications of AI for derivatives pricing. It's an application of a relatively well-known concept, reinforcement learning, but it's an application that's quite novel in ways that I'm going to describe and very much related to some of the things that some of my co-authors and I did a number of years ago, so I'll come to that in a minute. The benefit, of course, as John mentioned as a conclusion, is that reinforcement learning actually is very fast. It's very easy from the implementation point of view, but it's computationally a little bit more demanding. An hour to train this particular reinforcement learning network with the GPU is nothing. And in fact, if you did cloud computing as opposed to doing it on a desktop or a laptop, you can do this in minutes. It would cost you a little bit more, but computationally, it's really a remarkable advance over some of the traditional methods. So what I'm going to do is to provide a little bit of context for these techniques and then talk a bit about what you might do to do some additional horse races and then maybe consider alternatives to supplement this. So the first point I want to make is what AI actually means in this particular context and how it ultimately developed the literature on neural networks. So how many of you can read this? No, it's not Icelandic. It may look like it. Anybody? Okay, well, how about this? Can you read this? Anybody want to give it a try? Yeah, pretty good. You're getting it. Exactly. The most hateful torment for men is to have knowledge of everything but power. These basically is a permutation of the letters. You couldn't read the top sentence because the words were jumbled. But when the order of the words correct, even though the individual words were scrambled, your brain could unscramble it. That's the power of human neural networks. For about 12 watts of power, your brain, in a matter of seconds, could actually unscramble that second sentence. And that's really what artificial intelligence experts have been trying to replicate for decades now. And so the idea behind an artificial neural network is to observe that the brain, the human brain, is comprised of about 100 billion neurons, and all working in parallel. And so if we could actually model the function of each of these neurons and hook them up in parallel, well, maybe we can get some cool stuff to happen. So in 1943, McCulloch and Pitts came up with the first mathematical model of a neuron. And they started with the biology of neurons, which looks like this. This is a neuronal cell. And you can see that it's got this long axon along which an electrical impulse travels. And it travels when it is properly stimulated by collecting inputs from the dendrites, and inputs X1, X2, X3, and so on. You got a bunch of inputs. And when those inputs exceed a certain excitation threshold, then this neuron switches on. It actually generates an electrical impulse to have your body do something. But if those inputs aren't strong enough to cause that neuron to activate, then it stays dormant. Dormant, active, 0, 1. It's a bit. And so if you model it mathematically, you've got a bunch of inputs, X, and each of these inputs get weighted by a particular sensitivity. And then you add up those inputs, and after you add up the inputs, you'll then get some kind of sum. And if that sum exceeds a certain threshold, then that gets activated. And that's modeled by this output formula right there. And there's an activation function that is 1 if the inside element is greater than a certain threshold, and it is 0 otherwise. This is the simplest mathematical model of a neuron, and it is called a perceptron. That's what McCulloch and Pitts came up with in 1943. Now, that by itself is not so exciting. The magic happens when you take one of these simple objects and you replicate that 100,000 times over into multiple perceptrons. And then you combine those, add them up, and if they exceed a certain threshold, then that switches on and off. And then you do it again in another layer and another layer and another layer. And before you know it, you've got a neural network that can do some interesting things. So there are two generalizations for what I just described. One is the activation function. What tells you whether or not a particular neuron gets activated? It's not just 0, 1 in the more sophisticated cases. There's a logistic function that allows you to model partial activation. That's one generalization. But the more important generalization is we're going to have a lot of neurons. And we're going to have a lot of them not just arranged in one particular dimension, but layer upon layer upon layer. In fact, the human brain, the neocortex, the part of the brain that's responsible for cognition, is actually 6 layers, 6. And there are hundreds of millions of neurons in each of those layers interacting with each other. So that's where modern AI is. And about 15 or 20 years ago, some computer scientists at the University of Toronto, among other places, came up with the idea that instead of using one very, very long layer of neurons, if we had just 5 or 6, you would get deep learning, meaning that you could approximate really complicated phenomenon using this kind of network architecture. Okay, so that's where we are today. What can neural networks do? And the answer is pretty simple. From the computer science perspective, they can approximate really complicated decisions. Not sure how they do it, but the fact is they can do it. Now, from the economics and statistics point of view, it's a very different perspective. The idea is this is a nonlinear estimation methodology, non-parametric nonlinear estimation. And Hal White, the famous econometrician, wrote a book on artificial neural networks with this alternative interpretation, not computer science, but statistics. The problem with statistics is that although you can show that neural networks can approximate any nonlinear function that you choose, the fact is that you can't use statistical inference to interpret significance. There's no way to do a t-test of whether or not neuron number 125 in the 3rd layer is really important, because that statistical hypothesis test depends upon all of the other layers and whether or not those coefficients are 0 or 1 and when they switch on or off. So it turns out that there's been this big cultural divide between statisticians and economists on the one hand, and computer scientists on the other hand. And as a result, it's sort of slowed the growth of applications of AI in finance. And that's why this is such an important paper, because you've got a leading derivatives expert, John, who's working with co-authors to apply these techniques in finance. So what can neural networks do? Well, here's a nonlinear function. Does anybody know what this is? You recognize it? It looks like a negatively sloping line maybe, but maybe with a little bit of kinks here and there. It turns out that this is the sine function plus some noise. Now, you didn't know that, but if you applied a neural network to estimate this function, this is what you would get. The dark line is the estimate from the neural network. The dotted line is the actual function itself. With a relatively simple neural network, 5 nodes, 1 layer, this is what the sine function looks like. Now, the neural network looks like this. It looks nothing like the sine function. But who cares? It works. It's a good approximation. Now, economists would say, well, we care. We want to understand the deep structure of the underlying phenomenon. And if that's the case, then this is going to be a problem. But if you don't care, it turns out there are a lot of advantages. For example, the software, the code that generates one of these neurons is given by 3 lines. So if I wanted to do a 5-layer, 3,000 node network, it would take me approximately 15 lines of code. I can program that now in about 30 seconds with ChatGPT. And so for derivatives models, question, what if Black, Scholes, Merton, God forbid, were never born? Would we have been able to figure out the formula? Could neural networks have come up with that? And the answer was given by a paper that I co-authored with a couple of computer scientists here at MIT, Tommy Poggio, and then our student, Jim Hutchinson. We simulated Black, Scholes, Merton's prices and trained a simpler version of neural networks, not the fancy stuff that John is using, but basically a simple multi-layer perceptron. And the question is, can Black, Scholes, Merton be learned by this neural network? And the answer is yes. But it doesn't look like Black, Scholes. This is what it looks like. This is the neural network that approximates Black, Scholes formula. And in fact, it's an excellent approximation. It approximates it to within a few pennies. So the answer is, with a nonlinear structural form, you can approximate it with any kind of neural network. And in fact, if you apply it to data, you can show that for short-term options, for S&P options, we showed that for delta hedging purposes, a neural network is not as good as Black, Scholes. But for longer dated options, a neural network can actually beat Black, Scholes in hedging. So now getting back to John's paper and Jackie's paper, what they do is to basically point out that not all neural networks are created equal, and they use this reinforcement learning approach. And the basic idea behind reinforcement learning is you got a robot that's trying to figure out what to do. It'll make an action. The action will have consequences. You'll learn from the consequences, and you'll improve. That's the basic idea behind reinforcement learning. And this is the specific architecture of the model. The bottom line is that it allows you to reduce your cumulative errors over a period of time because you're learning from your mistakes. And it's similar in that spirit to dynamic programming, stochastic approximation, sequential decision-making, lots of things where you're basically doing fancy trial and error. So one suggestion as a horse race is to consider a dynamic programming approach where you start off with an arbitrary derivative payoff function, and you're going to use a delta hedging strategy to try to hedge that. And what you're trying to do is to minimize the sum of squared errors by using this self-financing strategy. And this is something that Leonid Kogan, Dmitry Bertsimas, and I wrote about in 2001. And what we show is that you can actually get some very good approximations, what we call epsilon arbitrage strategies, where you can get within epsilon of replicating a particular derivative using this dynamic programming approach. And so the question that comes to mind is, will this work better in certain cases, particularly because we're using a quadratic objective function? That means that what you're trying to do is to get as close as possible to the price, whereas with a one-sided loss function, you may not be as happy with the result if you're on one side of a trade versus the other side of the trade. So it might be worthwhile to consider these two-sided approaches and see whether that buys you anything. The other set of horse races you might run is to look at more complicated criteria function. Instead of just using VAR, you might want to consider skewness and kurtosis of your delta hedging portfolio, and that might give you a little bit more accuracy depending on what application you have in mind. Okay, so let me conclude with a couple of things. One is, what can't neural networks do? Because it seems like they can do everything. And here's something that it can't do. So imagine that we've got a particular commodity, and I'm going to show you the equilibrium prices at date 1, date 2, date 3, 4, 5, and so on. And I'm just going to give you the prices and quantities of this particular market. And it comes from, supply and demand, but I'm going to just give you the prices and quantities and ask a simple question. The simple question is, if you impose a consumption tax of 10%, what's that going to do to quantities and prices in equilibrium? Neural networks will never be able to figure this out. You can have an infinite amount of data, and you will not be able to estimate and recover the supply and demand curves with the neural network because you haven't gotten the structure of supply and demand. So I think this is where it's interesting to think about the confluence of human intelligence and artificial intelligence. It turns out that the most current forms of AI that have been the most successful, as in the case of breast cancer detection, are where you use AI together with radiologists who have a certain amount of medical knowledge about what they're looking at. It's not either or. In fact, if you look at the accuracy of radiologists by themselves, they're about the same as the accuracy of AI programs by themselves. But when you put them together, when you show a radiologist how to use AI programs, you actually increase the accuracy by about 35%. And so that's the bottom line. It's that this is an incredibly promising approach to applying AI in areas where it's not traditionally been applied. But I think the most success and where you can choose the different forms of hedging is where you understand a little bit more about the structure of the markets. And thank God Black, Scholes, and Merton were born, and they did what they did. All right, thank you. And happy anniversary.